Welcome to the Deep Dive, the place where we cut through the noise and get straight to the knowledge that matters.
Yeah.
For the last few years, the big story in AI has been scale up, making models larger, feeding them more data, building these incredibly sophisticated architectures. But now the frontier has really shifted.
It has.
It's no longer about sheer size, it's about control. We are talking about alignment.
That's absolutely right. When you deploy a large language model today, the user doesn't just want a factually accurate response. They demand a stack of diverse behaviors all at the same time.
A stack, yeah. Like what?
Well, they want safety, they want efficiency, they want the output to conform perfectly to some complex JSON or XML schema, and they want logical coherence. If any one of those fails, the model is basically unusable for that specific task.
So we've moved firmly into this realm of multi-objective optimization. We are way beyond simple accuracy. And for this, the industry relies really heavily on reinforcement learning from human feedback, or RLHF pipelines, which involve defining multiple distinct reward signals. You might have one reward grading the safety of the output, another one rewarding, say, adherence to a token budget, and yet another rewarding the logical flow.
And this is where the interesting paradox lies. A huge amount of cutting-edge research has been poured into designing these highly granular, really sophisticated reward functions. I mean, people are using GPT-4 to grade other models. They're using complex rule-based systems. The reward mechanisms themselves are incredibly advanced.
Right.
But the underlying engine, the thing that takes these beautiful, nuanced reward scores and turns them into a policy update, has been mostly, well, taken for granted.
So you're saying the optimization method itself, the algorithm trying to resolve all these conflicting preferences and maximize that stack of rewards, that's often the real bottleneck, not the reward design.
Exactly. The default workhorse for this, particularly in the open source community, has been a method derived from policy optimization, specifically group relative policy optimization, or GRPO.
And that, the authors of our source material argue, is the deep hidden flaw in the whole system.
It is. They suggest that when you try to juggle multiple, diverse, and, potentially conflicting preferences, the mathematical assumptions baked into GRPO introduce a fundamental systemic flaw in the learning signal. It loses critical information right before the model is even supposed to learn.
Okay, let's unpack this. Our mission today is a deep dive into a major paper from NVIDIA and its collaborators who pinpointed this exact optimization issue and proposed a pretty radical fix. We're exploring GDPO. Group reward-Decoupled normalization policy optimization. We're going to dedicate significant time to understanding precisely how GRPO fails, a process the authors call reward signal collapse. How GDPO fixes it through this really clever structural change called decoupled normalization. And then we'll drill down into the dramatic empirical results across critical LLM tasks like tool calling, math reasoning, and complex coding. This isn't just a tweak. It's a re-examination of the foundational math of alignment.
Let's start at the fundamental level of the standard practice. Group Relative Policy Optimization, or GRPO. It has become incredibly popular for RLHF training because, unlike older, more computationally intensive methods like PPO, Proximal Policy Optimization, GRPO, is just highly efficient.
And what's the major efficiency win there? I mean, why do people prefer it over something like PPO?
The key efficiency gain is that GRPO eliminates the need for a separate value model. In PPO, you need a critic network, that's the value model, to estimate the future expected reward of a state, which is then used to calculate the advantage, how much better a certain action was than expected. Training and maintaining that value model adds significant overhead and complexity.
So how does GRPO get away with not needing that critic?
It substitutes the value estimate with a relative comparison. For any given input prompt, the model samples a group of responses, which we call rollouts. Instead of comparing the reward of a single rollout against an external estimated value, GRPO compares the aggregated reward of that rollout against the average reward of all the other responses in that same group.
So it's calculating a group relative advantage estimate.
Yeah.
It's basically saying, how much better or worse was this specific answer compared to the other answers I just generated for this same question?
Precisely. The calculation involves subtracting the group mean from the reward score and then dividing by the group standard deviation. This local comparison within the batch of generated responses helps reduce variance and provides a stable, efficient advantage signal.
Yeah.
It's a very clever technique when you are dealing with a single, clear objective.
But when you try to apply this elegant, efficient mechanism to the messy reality of multi-objective alignment, things break down. How does the industry typically try to force multiple rewards, $2 or $2 all the way to level, into this framework?
The standard, intuitive, and ultimately flawed strategy is aggregation. You simply sum all the individual rewards, safety, format, length, coherence, into a single aggregated reward score, so dollars. You then just treat ERC as the single objective and apply the standard GRPO normalization process to it.
And the paper's central finding is that this aggregation step, this Dwarsa modeller, is the point of no return. It causes what they term the reward signal collapse.
Absolutely. The moment you sum those rewards, you destroy the granular information about which objective contributed how much to the total score. When GRPO then normalizes this summed score, that loss of resolution is solidified into a completely inaccurate advantage signal for the model.
Okay, here's where it gets really interesting, and I think we should slow down.
Yeah.
We need to walk through the paper's primary illustration of this collapse, because it's the ultimate aha moment for why GRPO is just fundamentally unsuited for these multi-objective tasks.
Let's take the simplest scenario imaginable, which is what the authors used to demonstrate this. We have just two binary rewards, R1 and 2102. You can think of $3 as safety compliance and $2 output format compliance. Each can only score a 0 for a fail or a 1 for a success.
Okay.
And we sample only 2 responses or rollouts for a single question, so G equals 2.
In this setup, the total aggregated reward, the roast dollar, which is just $3 plus R22, for any single rollout can only be 0, 1, or 2.
Exactly. Now let's look at the group comparisons. We are comparing the total rewards of our 2 rollouts, which we can list as pairs of total rewards. For example, RSM2.
And we are particularly interested in rollouts that should intuitively produce very different learning signals. Let's compare 2 specific combinations. One for $1 and dollars versus $2 20s.
Okay, so in the combination, the first rollout failed entirely, right? It scored 0 total reward. The second rollout scored 1 total reward. Maybe it satisfied 21 all, but failed 22, or, vice versa.
Right. But in the combination, $2 2, that first rollout still failed with a 0. But the second rollout scored a perfect 2. This means the second rollout satisfied both $2 and $20 at the same time.
Intuition dictates that the policy update should receive a much stronger positive learning signal from the $2 comparison than from the $2 comparison.
Yes.
A response that nails both objectives, a total reward of 2 relative to a failure, a total reward of 0, is fundamentally more valuable than a response that nails only one objective relative to a failure.
But GRPO, by aggregating and then normalizing these raw sums, it just loses this distinction of magnitude.
It does, completely. When you apply GRPO's normalization formula, subtracting the group mean, dividing by the standard deviation, the distinct reward combinations of $2 and $2, and even the combination 1, 2 all collapse into the identical non-zero normalized advantage pair. 1.707071, $1.7071.
That is astonishing. So a 1-point improvement, a 2-point improvement, and a 1-point improvement from a higher baseline, they all treat it as mathematically equivalent in terms of the strength of the learning signal they produce.
The information is it's compressed and corrupted. It's like taking a high-resolution, multi-channel audio file and saving it as a low bitrate MP3. The basic melody is there, but the richness and the distinction between instruments are completely lost. The model is effectively being told that getting a score of 1 is just as good as getting a score of 2 relative to a baseline of 0.
And if we look at the other extreme, what about combinations where the total rewards are equal, like $2 1 or $2?
They all collapse completely to an advantage of $2.
So no learning signal at all.
None. If one response fails both objectives and another succeeds at both, GRPO treats them as equally good or equally bad relative to each other, so it provides 0 gradient to push the model towards higher reward states. This fundamental masking of relative excellence is why GRPO leads to suboptimal convergence and, as we'll see, catastrophic instability when it's faced with conflicting or easily satisfied objectives.
So the GRPO framework is structurally incapable of preserving the necessary granularity to differentiate between good enough and truly excellent, when excellence means satisfying multiple criteria at once.
Exactly. It uses a lossy compression technique on the reward signal itself.
Now, you mentioned that some variants of GRPO, like those used in systems like Dr. GRPO or DeepSeek v3.2, try to tweak the normalization. Specifically, I think you said they remove the standard deviation term in the denominator. Why was that change introduced, and did it help with this collapse?
Well, that modification was originally introduced primarily to mitigate what they call question difficulty bias. In standard GRPO, if a question is inherently easy, the standard deviation of rewards across rollouts will be low. Dividing by a tiny standard deviation can lead to an artificially inflated advantage signal for really small reward differences. Removing it was supposed to temper these variances.
Did it accidentally fix the reward collapse?
In our simple two-rollout example, removing the standard deviation does provide a slight improvement. For $2 and $2, it separates them into distinct advantages, down to $5 and $1, $1 respectively. So you now have a stronger learning signal for the $2 to dollar combination, which is good.
But the paper found this wasn't a generalized fix, right?
Correct. When they scaled this up, when they increased the number of rollouts, or critically, increased the number of individual rewards being optimized, the variant without standard deviation offered only, I think the paper said, modest improvements in increasing the number of distinct advantage groups compared to standard GRPO. The underlying information loss from that initial aggregation step was still just too significant.
And it wasn't just an insufficient theoretical fix. As we're about to see, this modification also introduced really serious stability issues.
It did. It highlights that the solution requires a deeper structural change to the optimization pipeline, which, brings us to the innovation here.
Okay, let's transition now to the proposed solution. GDPO, Group Reward Decoupled Normalization Policy Optimization. This method is fundamentally about changing the order of mathematical operations to preserve that lost resolution.
GDPO operates on the principle that the relative strength of each individual objective must be calculated before those relative strengths are combined. It introduces 3 critical steps that differentiate it from GRPO.
Let's break down the methodology, starting with the core fix, decoupled normalization.
So, decoupled normalization is the answer to the aggregation problem. Instead of immediately summing the raw rewards $40 through $3 into a single compressed order, GDPO applies a group-wise normalization procedure, subtracting the mean and dividing by the standard deviation, to each individual reward separately. So, for reward $4, let's say safety, you calculate its group relative advantage $8 using only the core dollar scores across the rollouts. Then you do the same for $2 format, getting $2 and so on, until another.
So the resulting individual advantage, AA, preserves the exact distinction and resolution related only to that specific objective's performance within the group of rollouts. We now have a vector of normalized advantages, $, $2, all the way to 1L.
Precisely. This vector of advantages retains all the necessary information about which objectives were satisfied and how much better or worse they were compared to the group average on that specific dimension.
Then comes step 2, aggregation. Since we've already preserved the distinction with normalization, now we can safely combine them.
Yes. The policy update advantage is then calculated by summing these normalized individual advantages. The model receives a blended signal, but crucially, this blended signal is far more precise because it was constructed from high-resolution components. It's totally unlike GRPO, which blended raw data and then applied lossy compression.
And the final step, the one necessary for stability, is batch-wise normalization. Why is this required, especially if we've already normalized each component individually?
This step is vital for preventing training instability when you scale up the number of rewards. Imagine you are normalizing rewards 4-to-1 through 3-to-$. If you simply sum up 50 individually normalized advantages, $1 plus dots plus A50, the total magnitude of that final advantage signal, A show, will naturally grow as you increase the number of objectives, even if the model isn't actually performing much better on average.
That makes perfect sense, but it's like turning up the volume dial on the learning signal just by adding more instruments to the orchestra. The sound is louder, but not necessarily better.
Exactly. A constantly increasing advantage magnitude can lead to catastrophic policy updates. You could overshoot the target minimum or maximum or just completely diverge. By applying a final batch-wise normalization to the aggregated advantage sum, GDPO ensures the final numerical scale of the advantage signal remains stable and consistent, independent of how many rewards are being juggled. And the authors show in their appendices that without this step, convergence failures are pretty common.
So GDPO is a holistic solution. Decoupled normalization for precision, followed by batch-wise normalization for stability. Let's revisit that collapse example, $1, and see the power of this decoupled normalization in action.
Right. If you recall, GRPO matched both of those combinations into the same advantage signal, that 1.7071, 1.7071, $1.71 GDPO, because it normalizes $1 and $3 separately before summing their advantages. It successfully differentiates them.
So the combination where one objective was satisfied produces the normalized advantage pair of 2.70700 equals 70702.
While the combination $2, where both objectives were satisfied, produces the substantially stronger signal of $1.41422, $1.4142. The magnitude is doubled. It correctly reflects the fact that the second rollout was twice as successful as the first, relative to that zero baseline.
And that magnitude difference is the precise gradient information that GRPO just threw away. GDPO successfully assigns distinct proportional advantage values to each meaningful combination of successes and failures.
And they actually quantified this difference empirically using a metric for granularity. They tracked the number of distinct advantage groups produced by GRPO, GRPO without standard deviation, and GDPO as they varied the number of rollouts and the number of rewards.
And what did those granularity graphs show?
They showed that GDPO consistently maintains a substantially larger number of distinct advantage groups across all tested configurations. As the number of objectives or rollouts increases, GRPO's number of groups just flatlines, which indicates collapse. Meanwhile, GDPO's number of groups continues to rise, demonstrating its ability to preserve resolution. This increased granularity is the theoretical key to more robust, precise, and expressive advantage estimation.
That gives us a really rock-solid theoretical foundation. The claim is that GDPO provides a higher resolution map for the model to follow. Now let's see if that high-resolution map actually translates into real-world performance gains, starting with a classic multi-objective task: tool calling.
Tool calling is an excellent first test case because it requires compliance on two very distinct, non-conflicting axes. The LLM has to intelligently decide which external tool to use and how to use it, but it also has to adhere strictly to a predefined, often complex output format like required tags, strict ordering, specific bracket usage, things like that.
What were the specific rewards they defined for this task?
There were two. The first was the correctness reward, mathcalcorrect, which was a continuous floating point score between -3 and 3. This is the sophisticated, high-effort reward that checks the reasoning, the tool name matching, parameter matching against the ground truth.
Okay.
The second was the format reward, mathcal format, which is just a simple binary score, a 0 or a 1, checking if the output structure is compliant with the required schema.
So a highly complex, continuous reward mixed with very simple, discrete compliance reward. A classic scenario for GRPO collapse.
It is. The setup involved training Qwen 2.5 instruct models, both 1.5B and 3B, on a large combined tool use dataset for 100 steps. And the training convergence curves, which are figure 4 in the paper, are fascinating.
What did the dynamics tell us about the learning process?
GDPO consistently converged to significantly higher correctness and format scores across the board. In the early stages, GDPO showed faster improvement on the correctness reward, which suggests the model was rapidly finding the right tool use strategies. But crucially, GDPO maintained better momentum towards the end of training, achieving superior final compliance scores on that binary format reward.
And it's often those subtle objectives, like strict format compliance, that get washed out when continuous rewards dominate the aggregate signal. Decoupled normalization should allow that simple binary success signal to stand out more clearly, even when it's mixed with that complex correctness score.
Exactly. And the downstream evaluation confirms this. When they tested the trained models on the industry standard Berkeley function call leaderboard, BFCL v3, the performance gap was just clear as day.
What were the numbers for the smaller Qwen 2.5 Instruct 1.5B model?
GDPO showed a strong, consistent victory. It achieved roughly a 2.7% improvement on the overall average accuracy compared to standard GRPO, but the real gain was in that subtle objective. GDPO achieved over a 4% improvement in the correct format ratio. It hit 80.66% compliance versus only 76.33% for GRPO.
No.
And for the 3B model, GDPO also outperformed GRPO, proving the decoupled signal is effective even as the model scales.
So GDPO allows the model to be both smarter in its reasoning and more meticulous about packaging that reasoning correctly. That fidelity to the binary compliance reward is a direct consequence of preventing signal collapse.
It absolutely is. This is not just theoretical math anymore. It's an improvement in real-world real-world usability. If you are building an agent that relies on perfect JSON output for integration into a pipeline, a 4% compliance boost is monumental.
Now, let's revisit that critical ablation study, the one where they removes the standard deviation term from GRPO, the GRPO without standard deviation. The math looked a little better in simple cases, but what did the tool calling task reveal about its stability?
This is perhaps the most damning piece of evidence against just tweaking GRPO. Recall that GRPO without standard deviation showed similar correctness reward gains to GDPO during training. It looked competitive on the difficult task. However, when evaluated on BFCL v3, this variant resulted in a catastrophic failure, a 0% correct format ratio, which is documented in Table 2.
0%. So the model failed entirely to learn the required output structure.
The instability caused by removing the standard deviation, which was an attempt to mathematically increase signal diversity, it introduced such numerical chaos that the model could not successfully converge on one of the required objectives. Even though that objective wasn't conflicting with the main one, it effectively derailed the entire format objective.
And this emphasizes why GDPO's stability component, that final batch normalization step, it's not a luxury, it's a necessity. GDPO uses decoupled normalization for precision and then batch normalization to rein in the magnitude and ensure stability, and that's how it achieves both high accuracy and high compliance.
It's a beautifully balanced solution. It solves both the resolution issue, the collapse, and the stability issue that arose when attempts were made to fix the resolution issue in isolation.
Fascinating. So, tool calling tests how well an optimizer handles distinct, non-conflicting objectives. Let's move to a much harder scenario, math reasoning, where the objectives are intrinsically antagonistic. They're competing.
This is the real stress test. In math reasoning, we are demanding two things that push the LLM in opposite directions. First, maximize the correctness reward, math correct, which is binary, a 0 or a 1. Solving hard math requires detailed step-by-step reasoning, which naturally leads to long responses.
Right.
Second, we enforce an efficiency constraint, the length reward, math cur length also, which is achieved only if the response stays below a specific token limit. I think it was 4,000 tokens in this study.
So the path to high correctness tends to violate the efficiency constraint. It creates this inherent trade-off the optimizer has to navigate.
Right. The setup involved training DeepSeek R1 and Qwen 3 models on a competition-level math dataset for 500 steps. And we really need to analyze the training dynamics shown in Figure 5 for the DeepSeek R1 1.5b model because it reveals the core challenge of multi-objective alignment.
And that challenge is what they term the easy reward problem.
Precisely. It's classic optimization behavior. Both GRPO and GDPO rapidly maximize the length reward, the math call, within the first 100 steps.
Why is that?
Because satisfying a simple length constraint is logarithmically easier than solving a complex math problem correctly. It's the low-hanging fruit.
And this rapid, early maximization of the easy reward coincides with a temporary but noticeable drop in the correctness reward. The model quickly learns the efficiency constraint and then struggles momentarily to balance that with the challenging accuracy goal.
That initial trade-off is unavoidable. However, their training paths diverge dramatically around the 400-step mark. GRPO training visibly destabilizes. Its correctness reward score begins a clear decline, which indicates a partial collapse of the learning process on the critical objective.
So this is the reward collapse manifesting as a training failure. The learning signal is just too fuzzy to guide the model successfully up the hard accuracy gradient while maintaining the constraint.
Exactly. The compressed signal fails to provide sufficient contrast between a decent answer that respects the length limit and a truly great answer that respects the length limit. And furthermore, while the median response length remained acceptable for GRPO, the authors tracked the maximum response length within each batch. For GRPO, this maximum length started increasing sharply after 400 steps, showing a failure to adhere to the constraint under challenging or boundary conditions.
So GRPO starts losing control of the easy objective it had already mastered, while at the same time failing to make further progress on the hard objective. That's a total loss of control.
Contrast that with GDPO. GDPO recovers the correctness reward much more effectively, continuing to improve it steadily throughout the rest of the training cycle. And critically, it maintains superior control over the efficiency objective. Its maximum response length consistently decreases over the 500 steps. It shows the model is learning to be both accurate and efficiently concise.
Moving to the evaluation results on major benchmarks like AIM, Math, and Minerva, what was the bottom line on this accuracy-efficiency trade-off?
Well, the data in Table 3 proves that GDPO achieves a far superior trade-off. GDPO-trained models demonstrated substantial improvements in reasoning efficiency, sometimes achieving up to an 80% reduction in the percentage of length-exceeding responses on benchmarks like AIM, while simultaneously boosting accuracy on most tasks compared to GRPO.
Let's focus on the AIM benchmark, which is notoriously difficult. What did the 7B DeepSeek model show there?
The DeepSeek R17B performance gap was significant. GDPO improved accuracy by nearly 3 percentage points over GRPO. It reached 53.1% accuracy compared to GRPO's 50.2%. But the efficiency metric is equally crucial. GDPO reduced the length exceeding rate to a mere 0.2%, down from GRPO's 2.1%.
That is nearly an order of magnitude improvement in constrained adherence, while delivering higher accuracy. That level of control suggests the model is receiving a high-fidelity gradient that precisely defines the acceptable trade-off boundary.
It shows that decoupled normalization gives the model the clear signal it needs. It's like it's saying, this answer scored high on correctness, and yes, it respected the length limit, giving it a much stronger relative advantage than an answer that was only correct but too long. GRPO just couldn't provide that clear feedback without washing out the signal.
The lesson here is clear. For real-world application, where alignment almost always involves managing tension between objectives, stability, and precision are paramount.
Yep.
Now that GDPO has proven it can handle antagonistic rewards, let's move to the complexity of human priority. Because in practice, we rarely treat all objectives as equally important. How do we encode the idea that one reward, say safety, is 10 times more important than conciseness?
This is the next level of alignment challenge. The authors investigated 2 methods for enforcing priority, particularly given the large disparity in difficulty between the easy length constraint and the challenging accuracy objective.
And the most obvious way to set priority is just through simple reward weight adjustment.
That's what they tried first. They fixed the challenging correctness reward weight at 1, y correct 1, and then varied the easy length reward weight downwards. They were trying to demote the importance of the length constraint. The weights varied from 1.0 down to 0.25.
Okay, so if you reduce the weight of the length reward, the model should naturally focus more on maximizing the correctness reward, even if it means sacrificing a perfect length score. Did the model behave rationally?
Surprisingly, no. For both GRPO and GDPO, reducing length to $0.75 or 0.5 had, I think they said, little impact on the length exceeding ratio. The model continued to hit the easy constraint regardless of the moderate weight difference. This is a critical finding. The inherent ease of satisfying the objective was a more dominant factor than the relative weight assigned to it.
That's a cognitive bias coded right into the optimization process. The model just prefers the low-effort win, regardless of the relative score.
It confirms that simple weight adjustment alone is an ineffective prioritization tool when there is a significant difficulty disparity between objectives. The weight difference has to be massive just to counteract the inherent ease of the task. They only observed a substantial increase in the length exceeding ratio, meaning the constraint was relaxed as intended, when length was reduced all the way to 0.25.
So if simple weighting is unreliable for prioritizing difficult tasks, what structural solution did they propose?
They moved from simple weighting to a conditioned reward function. They introduced the conditioned length reward, denoted tilde length. The key difference is that this reward is only received if the response length is satisfied. And D, the correctness reward is also achieved. Math correct all has to equal 1.
That changes the game entirely. You are now making the easy reward dependent on the difficult reward. You force the model to solve the hard math problem correctly first, and only then does it get credit for being concise.
Exactly. This structural change immediately mitigated that easier reward problem we saw earlier. If you look at the training curves in Figure 7, using tilde length prevents the aggressive early maximization of the length reward. The correctness score still dips slightly, but it avoids the large destabilizing drops seen with the simple length reward.
By forcing the model to solve the difficult problem first, you align the reward structure with a desired human priority. But did GDPO still leverage this conditioned reward structure more effectively than GRPO?
Absolutely. When they evaluated performance using the conditioned reward, that's in Table 4, both optimizers saw a better relaxation of the length constraint compared to simple weighting. However, the limitation of GRPO's signal collapse became even more obvious. GRPO largely failed to convert this relaxed constraint into meaningful accuracy improvements. It just missed the opportunity to focus on the difficult objective.
It seems like GRPO still couldn't properly calibrate its advantage estimates when the condition reward structure made the signals even more sparse and complex.
That's the interpretation. But GDPO, with its high-resolution decoupled normalization, effectively capitalized on the relaxed constraint to drive accuracy higher. Using tilde length with GDPO yielded a massive 4.4% accuracy improvement on the AM benchmark compared to GRPO using the same condition structure. And GDPO showed consistent accuracy gains across all benchmarks under this structure, while GRPO showed inconsistent or minimal gains.
So the ultimate lesson on priority variation is a two-step approach. First, use reward conditioning making the easy reward contingent on the hard one to overcome inherent difficulty disparity.
That's the structural alignment step. And the second part of the lesson is that once you've structurally mitigated that difficulty gap, then GDPO's precision allows you to use standard reward weights to make fine-grained priority adjustments. The authors showed that when they adjusted the weight of the conditioned reward, the resulting changes in length violations behaved predictably, which was not the case with the original unconditioned reward.
GDPO's ability to faithfully interpret these complex condition signals makes it the necessary optimization method for achieving these nuanced, high-priority alignment goals.
It guarantees that the effort put into designing these clever structural rewards isn't just wasted by a flawed optimization process.
For our final empirical check, we need to verify the generalizability of GDPO when we scale up the number of rewards. We're moving now to the coding reasoning task, a highly complex domain, and we're optimizing for 3 distinct objectives.
This is the ultimate test of complexity management. We are training DeepSeek R17B on a coding dataset, requiring it to be accurate, efficient, and robust. We introduce 3 simultaneous rewards. 1, the pass rate reward, mathcaldon, measuring how many PES cases the generated code passes.
Okay.
2, the condition length reward, tilde length n to manage efficiency. And 3, the bug reward, mathpilon, which is a binary reward checking for runtime or compilation errors.
So the model needs to balance functional correctness, conciseness, and code stability, a genuine trifecta of real-world requirements. How did GRPO and GDPO compare under 2 and 3 objectives?
First, they looked at the 2 objective scenario, just pass rate and length. GDPO, or GDPO2 object, showed consistent gains. It improved pass rates across all coding tasks, apps, code contests, code forces, and Taco compared to GRPO2 object, while maintaining an equivalent or better length exceeding ratio.
Can you give me a concrete example of that 2 objective win?
Yeah, on the difficult Taco benchmark, GDPO achieved a 3.3% pass rate gain over GRPO and simultaneously reduced length violations by 1%. That's a clear indication that GDPO is finding policy updates that are simultaneously better on the hard objective and tighter on the constraint.
And when they added the 3rd, non-overlapping objective, the bug reward.
This is where the true power of decoupled normalization for complexity management really shines. GDPO, the 3-objective version, achieved a substantially better overall balance than GRPO3 object across all 3 objectives. It maintained a high pass rate, similar to GRPO's, but markedly reduced both the length exceeding ratio and the bug ratio.
So GRPO managed to maintain a decent pass rate, but only at the cost of higher rates of bugs and longer, less efficient code. GDPO found a way to satisfy the difficult correctness objective while optimizing the 2 efficiency and robustness constraints simultaneously.
Precisely. On code contests, for example, GDTO reduced the bug ratio to 2.5%, down significantly from GRPO's 3.9%, and kept the length violations notably lower than GRPO, all while achieving comparable overall pass rates. When GRPO aggregated 3 different signals, the collapse was so severe that the model failed to efficiently optimize the secondary objectives. GDPO's high-resolution signal allowed the model to fine-tune its policy for all 3 goals.
This final set of results confirms that GDPO is not merely a niche fix for one task, but a generalizable principle. As LLM alignment demands more and more compliance goals, safety, honesty, efficiency, style, format, and so on, an optimization algorithm that can handle dozens of distinct signals without information loss becomes absolutely critical.
GDPO has really established itself as a more stable, accurate, and high-fidelity optimization method for complex, multi-objective alignment compared to the industry standard.
Okay, let's summarize this deep dive. We started with the current frontier of LLM training, where success depends on juggling a complex stack of human preferences. We found that this decades-old mathematical assumption embedded in standard RL, specifically the practice of aggregating multiple rewards before normalization in GRPO, fundamentally loses critical information.
This information loss, the reward collapse, means that distinct outcomes, like satisfying one objective versus satisfying two objectives, are treated as mathematically identical. This leads to a fuzzy, compressed learning signal. This is why GRPO leads to instability, suboptimal performance, and often just fails to converge successfully on secondary objectives, especially when they are non-conflicting, like format compliance, or competing, like length efficiency.
And the GDPO solution is structural, and it's elegant. It reverses the order of operations through decoupled normalization. By calculating the relative advantage of each individual reward separately, and only then aggregating those normalized signals, GDPO successfully preserves the distinct learning signals required for high-resolution optimization.
And the practical proof is overwhelming. GDPO led to higher format compliance and tool calling, where GRPO variants failed catastrophically on stability. It eliminated the training collapse and achieved a superior accuracy-efficiency trade-off in math reasoning. And it scaled successfully to 3 complex objectives in coding, achieving higher overall robustness and conciseness while maintaining high performance.
The significance of this paper is that the authors successfully shifted the focus. They forced the community to look beyond designing clever rewards and instead examine whether the optimization pipeline itself is mathematically fit for the complexity of modern multi-objective tasks.
So here's the provocative thought for you, the learner. If the quality of an LLM's alignment depends not just on what preferences we reward, but fundamentally on how those rewards are processed and compared within the optimization algorithm, we have to ask, what existing deployed LLMs might be currently performing suboptimally or failing in subtle ways? Like generating inefficient code or occasionally violating formatting rules simply because they were trained using underlying mathematical assumptions that compress their learning signal. It suggests a vast landscape of existing alignment efforts might need to be re-examined, not by changing the data or the architecture, but by changing the optimization math.
That truly highlights that sometimes the most cutting-edge breakthroughs come from questioning the algorithms we thought were settled science. That's it for this deep dive into GDPO. We hope this knowledge helps you see the world of LLM alignment with a new, higher resolution lens.